Okay, so welcome back to Vibrations in Acoustics. In this problem, we have a machine that's vibrating with a specific equation given. So this is its vibratory motion as given by the problem. This is in millimeters. This is alpha 50t a cosine. So I apologize for scrunching that up. We have two initial conditions. One is in millimeters, one is in meters. You'll notice the equation is in millimeters. So we have to find a and alpha, and then after that we need to redefine the equation in this format as opposed to this format, and identify what A1 and A2 are. So hopefully you've had a lecture or two explaining how the basic work of this goes, and I'll work this example here as easily as I can. So first thing I'm going to do is reform this equation so it's in meters, so that we have consistent units. So I'm going to go x of t is equal to a over 1,000 cosine of 50t plus alpha. And what I did was I divided by 1,000 so that now it's in the form of meters. This means that A is in millimeters, which will be a little bit useful later on. And I'll call this equation 1 for now. Okay, so then x of 0, which is equal to A over 1,000 cosine alpha, because t has gone to 0, is equal to 0.003 meters. Okay, because of the millimeters up here and the division by 1,000 again. So this means that this goes to a cosine alpha is equal to 3. I'm going to call this equation 2 for now. Alrighty, now we need to take the derivative and also set it equal to 0 in order to use our other initial condition, and that'll give us two equations so that we can solve a system of equations and figure out what both of these constants are. So that's the basic method. So I'm going to go ahead and work through that. So x dot of 0, we'll be using dots in all of my lecture videos on this, is minus 50a, because we take the derivative inside, outside, so minus 50a, over 1,000, sine, again, the derivative, the negative, the sine, and the 50 all come from taking the derivative of this equation. Sine of alpha is equal to 1. So then so this goes to a sine alpha is equal to negative 20. Okay, so we have these two equations. So then, if you want to use standard Euler format in order to solve this and solve for the coefficients, you generally have an equation where hang on, let me go at this a different direction. Euler's layout is AE I theta, basically. So we're looking for theta and A in this situation. So in order to do that, you use Pythagoras' theorem. A is equal to the square root of A plus B. And A plus B are these two equations right here. Okay, so then we've got a cosine alpha squared plus a sine alpha squared, all under the square root. Now, of course, these are both equal to certain values, so you can go ahead and plug in, what is this, 3 and negative 20 as these values under here, and you'll find out that A is equal to 20.2237 millimeters. And that's your value for A. Now, alpha, you use the inverse tangent negative 1, of a sine of alpha all over a cosine of alpha. Okay, and again, you sub in the values for these, which are 3 and negative 20, or negative 20 and 3. So you get the inverse tangent negative 1, of negative 6.667, and that solves to negative 81.47 degrees, which is equal to negative 1.4219 radians. And if you don't know how to work with radians, you should get used to it, because in vibrations, radians are always handier, and the conversion is pi over 180 times degrees if you're ever lost on that. Okay, so now you have alpha and the a. So that means that x of t, the coefficients of it, are equal to 20.22 cosine of 50t minus 1.4219. And that's all you have to do. You've solved for the coefficients of a and alpha. So basically all you have to do is take the initial conditions, make sure you solve the equations correctly. Once you have these equations, we'll call this equation 3, these two equations, you can go ahead and sub them into the basic equations for finding the a and the alpha based on Euler's. And then you can continue on. The reason this works is because you have a cosine and a sine, which are the real and the imaginary parts of a particular problem, because this is equal to a cosine of theta plus a sine, I sine theta. I'm going to put an I right here. So that's where this comes from. This is why we suddenly were magically able to take these two equations, because we have two cosine equations essentially that follow Euler's equation. And using Euler's equation, you're able to use the Pythagoras' theorem in order to solve out for amplitude. And if you watch my addition video, I do a quick little show of the triangle that makes this possible, and that'll help it make a little more sense too. But this is basically the equation that allows for this substitution to happen, to take this and sub it into here and solve for these coefficients. So that's how you figure out those coefficients. Now we had to change it, express it in the form of a1 cosine of omega t, a2 sine of omega t. Well, you would think, well, I just had it, I just explained what it was, we can just add those together. It's not quite that easy, but it's pretty close. So, in order to do that, we have cosine of a plus b. This is how we're going to lay this out. So we've got cosine of a, cosine of b, minus sine a, sine b. So I just set up a basic trig identity. Try to be as familiar with these as you can. So we're going to use equation 1. Using equation 1, we can express it as x of t is equal to, I'm going to go ahead and show you equation 1. Equation 1 right here is the very first home equation that we used. Okay. X of t is equal to a cosine 50t cosine alpha minus a sine 50t sine alpha. Okay, so go ahead and looking at this. The equation right here is the coefficient cosine 50t plus alpha, which is the equivalent of cosine a plus b. That's how I know we're able to use this identity. Take this identity, expand it out, and then you sub in the values that are here. So 50t is a, and then b, just like this. Sub it into the identity. Now you can simplify it a little bit, and you can go a1 cosine of omega t plus a2 sine of omega t. And we know that omega is equal to 50. That means that a1 is equal to a cosine of alpha, and then a2 will equal negative a sine of alpha. Hopefully you can see how that works. Right here, sine of alpha, omega is equal to 50 because we spread it out through the entire deal there. Looking at this, we're just relating these two equations. We know that this equation is the same as this. This is all cosine. You can basically factor out this cosine, then you have a1, factor out the sine, you get a2. You see that 50 and alpha are the omega and the alpha. So then omega is equal to 50, and a1 is equal to cosine, and so on and so forth. So I hope I didn't skip too many steps right here, but you basically just factor out this cosine, factor out this sine, and you have the final stuff that you want right here. Just about like that. Okay, so now going from here, it's pretty easy to go to x of t. So therefore, x of t is equal to 3 cosine 50t plus 20 sine 50t. And it's in millimeters because we didn't have that conversion earlier on. And that is how you express it as in the A1, A2 format, as opposed to just a single equation with a sign. So hopefully that was helpful. The biggest trick right here is seeing the trig identity that you're able to use, expanding it out, then basically factoring and pulling out the parts that you can, and then identifying what you need, what you can use, and you have all the pieces that you need. Alrighty, and that's how you create an equation from a basic equation of motion for a harmonic system.